palatable butterflies. In other words, they're getting a survival advantage by looking like something that's distasteful to birds. And he saw this repeatedly in various groups of butterflies. So this form of mimicry, when Bates explained it to Darwin, Darwin was absolutely delighted. He thought that Bates's paper on mimicry was one of the most remarkable papers he had ever read. And as Darwin's work unfolded in later years, he would incorporate this additional work from naturalists into the whole fabric of evolution that he was describing. Now, Bates wrote just one book called The Naturalist on the River Amazons. It's still widely available today. You can find it in paperback form. And I encourage you to read books by these 19th century naturalists because they describe a world being sort of discovered, at least by educated Western individuals for the first time. They also describe a world that sadly is not the same as it was 150 years ago. I have a little more to say about that later. Bates was also a little bit of a poet. He was a great artist. And just as with Darwin, and I think somewhat influenced directly by his correspondence with Darwin, there are various passages in The Naturalist on the River Amazons that sort of wax poetic about evolution. And here's one. Bates talks about how on these expanded membranes, speaking of butterfly wings, nature writes as on a tablet the story of the modifications of species. So I want to focus on, in the first part of my talk, is that story. How are species modified? What can we learn? And we will, in fact, talk about the markings on butterflies. But I don't want you to go away thinking at all that this is just about butterflies. Just as with the stickleback work that David's described, what we can learn from individual species like butterflies or fruit flies, as you'll see, offers general insights into the making of the whole kingdom, the sorts of mechanisms that are at work everywhere. And what scientists try to do is find the best models, the most tractable models that will give us these first principles. So we're going to focus on the question of how new patterns and how new features arise. And it's a little bit different than, for example, the hind fin reduction in sticklebacks. We're going to really ask not how something goes away, but how something new evolves. Now, wings have been an evolutionary tablet throughout the insects, not just butterflies, not just moths, not just beetles, if you're familiar with things like ladybugs, but even in the more humdrum fruit fly world, wings have acquired all sorts of markings in the course of the evolution of these species. So you're probably most familiar with fruit flies, these annoying little nearly invisible things around your bananas in the morning, or maybe you've had a chance to handle them in the laboratory, and if you did, probably the species you handled was not too colorfully marked. But throughout this group of flies, there's some fantastic markings, albeit in black and white. They have not discovered the color palette that butterflies have discovered. But they're nonetheless a great example of how new patterns arise continuously in evolution. So today I'm going to look at some simple patterns on insect wings. I'm going to look at spots and frame a simple question. How and why did fruit flies and butterflies get their spots? Now we're going to look at a simple black spot that occurs on certain fruit fly wings and some beautiful concentric rings, colored rings of spots that occur on butterfly wings, and get insights into how these new patterns have evolved and what that teaches us in general about innovation in the course of evolution. Let's look at a couple fruit fly species. These are two fairly closely related species. I'm showing you just the male flies, their whole body sort of looked at from the top-down view on the left, and their isolated wings shown over on the right. Well, the obvious difference between these two species is that one has spotted wings and the other doesn't. In fact, you'd be pretty hard-pressed if you could examine the rest of the body of these flies to find almost any other difference. So there's this very pronounced difference. And these are the males of the species, and only the males of the species, and the bottom species here called Drosophila biarmapace, only the males have these wing spots. So before I get at the how, let's get at the why, and that's shown in the next short video. Look at the top of the fly with the spots, and that's a little dance that he does in front of the female while he's pursuing her in courtship. So species that have these spots at the edges of their wings engage in this courtship display. Now, courtship display is really directly connected, of course, to the process of mating and passing genes on to the next generation. So courtship display is a form of what's called sexual selection, a term coined and described by Darwin at length in his 1871 book, Descent of Man. So again, not just coral reefs, not just descent with modification, not just natural selection, sexual selection as well. And because sexual selection is operating at that moment of mating, or leading up to mating, it's one of the most powerful forms of selection that goes on within species. Pigmented wings have evolved many times, and this is just the isolated wing of another Drosophila species called Drosophila tristis. And we'll see in the next video that the idea is the same in terms of a courtship dance, it's just the steps are a little bit different. So if you see this male at the bottom is extending his pigmented wing, sort of in a matador sort of approach, sticking out its left wing. She seems to be paying attention. She maybe was not as impressed as she should have been. Hey, hey, hey. Now, I know you're all laughing, but, you know, I have teenagers, and I've been to some of your dances. And okay. So this courtship dance is an important display that the males do, and these sorts of displays are throughout the animal kingdom, usually the male displaying for the females, sometimes comical, sometimes pathetic, and often unsuccessful. So how did these spots evolve? And the simple message is something very closely related to what David's been saying. The simple message is it through the new use of a toolkit gene that these spots arise. So if you look at the left-hand side, these are 3 different Drosophila species. The one in the center is the one you've been looking at that has these spotted wings on the males. And on the right, we're looking at the developing wings inside the pupal case of these flies using special techniques that allow us to see where a toolkit gene is being used. Not the blue stain that David showed you, but in this case, the white pattern that you can see pointed out here with the arrow. That reveals where a particular toolkit gene is being used, and you can see it's being used exclusively in this species at very high levels in this part of the wing that's going to become intensely pigmented. Think of this toolkit gene as a paintbrush. And what this means is that there are genetic instructions in this species that instruct this paintbrush to be used in a part of the body that is not being used in other species. That's the novelty. That's the key change between these species, the spotted and the unspotted species. Now let me just go to the colorful version of the same story. This is an East African species of butterfly. Now the spots in this species are being used for a different reason. These spots are not being used to attract mates or to impress mates. These concentric rings of pigmentation are out towards the edge of the wing, true. But what they're doing is they're drawing the attention of predators, in this case, birds, away from the main body of the butterfly. The main body of the butterfly, of course, contains all its vital organs and its blood, and if that was to be damaged, it would probably be lethal. But the butterfly can tolerate attacks out at the edge of the wing. And this is an East African butterfly photographed in the wild here that has suffered an attack from a bird. And what you can see is a bird can take a pizza slice out of the wing, but the butterfly can continue to fly, and all its vital organs are protected. So this is really sort of a decoy bullseye. These false eye spots are to distract predators' attention away from the main body out towards the edge. So this is an adaptation for survival, not an adaptation for mating. Nonetheless, it's real important to the selective advantage of these butterflies, the survival and reproduction of these butterflies. So what do we know about the making of these spots? Well, again, advances in developmental biology that have taught us about the sorts of genes involved in building body parts and in patterning those parts have given us a whole toolkit of genes that are used in all sorts of species, and we know about the use of some of these toolkit genes in the making of butterfly wing patterns. What I'm showing you here is on the right are isolated wings from 2 species, the monarch butterfly, which might be familiar to you in the upper right, and this East African butterfly on the lower right. And on the left, we're looking at wings that have been stained in a special way to reveal where a particular toolkit gene is being used in the caterpillar. A week before, those wing patterns would be visible to the naked eye. So this is an image you can only see in a special type of microscope to allow us to visualize where genes are being used. This toolkit gene in the monarch butterfly is being used in all of the cells towards the edge of the wing, and those white flecks of pigment